In this presentation, we will continue our investigation of complex number operations. The objectives are to learn to calculate the absolute value of a complex number, learn to represent complex numbers in a new form, polar form. Up till now, you've learned the algebraic representation, which has been called standard form. In subsequent videos, because we're limited to 5 minutes in length, you will learn to multiply and divide complex numbers using polar form, find the power of a complex number using polar form, and find the roots of a complex number using polar form. And we'll represent many of these graphically to give you a visual representation of the complex numbers. Let's begin by looking at the absolute value of a complex number. Extending what we know from the real numbers, the absolute value of a real number is its distance from the origin on the real number line. That's graphed here. Let's extend this concept to a complex number. We'll define the absolute value of a complex number as its distance from the origin. However, looking at the way we graph complex numbers, they're graphed in a two-dimensional space, where the real numbers are graphed in a one-dimensional space. And here the real component is on the horizontal axis. The imaginary component is on the vertical axis. If we find the length from the origin to our complex number, a plus bi, we would need this dashed blue distance, which we'll call the absolute value of the complex number. This can be found by taking the square root of the components of the complex number squared. Well, we're really using the Pythagorean theorem. And these dashed red lines show you we can create a right triangle and find the length of the hypotenuse to find the length of z. That is just the Pythagorean theorem. Here's a simple example. To find the absolute value of z, we take 4 squared plus 5 squared, take the square root. Our result is radical 41. If you wish to look at an example, try number 5 on page 696. We can also represent complex numbers in what's called polar form. Up till now, we've used the algebraic standard form to represent our complex numbers. If you look at the graph of a complex number, it's in a plane, and I think you could see that we could create a right triangle to define the position of z. The length of this hypotenuse, which is the absolute value of z, can be found by finding a squared plus b squared and taking the square root. We call this the modulus. To find the length of a, we could have r cos theta. B would be r sine theta. We would need to know the angle theta, and that can be found from the inverse tangent of b over a. Theta is called the argument when we're in polar form. If we substitute the above results into the standard form, we obtain the following. R cos theta is a, r times sine theta would be b. We've just factored out the r to put it in this form, which is considered polar form. A plus bi is referred to as rectangular form. R cos theta plus sine theta is referred to as polar form. Remember, r is referred to as the modulus, and theta is the argument. Let's look at a simple example of the polar form of a complex number. Let's find the polar form of z equals 4 plus 4i. Well, we need the modulus r. We use the Pythagorean theorem to find that value. We need the angle theta. We use the inverse tangent of the components of z to find that value, which in this case is pi over 4. And we substitute those into our result for polar form. If you wish to try an example on your own, look at number 24 on page 696. Thank you.